Hello, this is Mr. Gilmore with the 10.7 Center, Circumradius, and Apothem lesson. Now, we are moving toward finding the area of regular polygons, which we'll see in our next lesson. But before we get there, there actually are several properties that we need to prove about the regular polygons. We've encountered regular polygons throughout our system, and we know that regular polygons are these polygons that are equilateral and equiangular. However, there are several pieces of information that we are going to need and to introduce in order to actually move toward finding the area derivation of our regular polygon. And so before we get there, we need to prove these properties to be true, which are going to lead us then in appropriate ways to find or derive our area polygon formula such that we don't jump to any conclusions, that we actually arrive to our valid reasoning through these provable properties of the regular polygon. So where we begin is actually introducing two vocabulary words. One is the center of a polygon, or center of a regular polygon. As it turns out, there is a point on the interior of our regular polygon that we call the center, and that center is defined to be the point that is equidistant from all of the vertices of the regular polygon. Now, the thing about defining something, remember, is just because we define this point does not mean this point actually exists. We need to prove that this point actually exists, which means part of the homework assignment tonight we will see that this center point is going to be the first thing we need to actually show is there, that it's going to be equidistant from the vertices of our regular polygon. Now, our main template we're going to be using for the notes is just going to be the hexagon. Now, however, really any regular polygon will work, and we are going to find that any regular polygon is going to have a center. And how we're going to do this is actually start with our smallest regular polygon, which is the regular triangle, and we'll be able to prove these properties to be true about the regular triangle, and then we can extrapolate those to apply to any higher order polygon. So within our regular polygon, we're going to prove that the center actually exists, that there is a point that is equidistant from the vertices of the regular polygon. Now, if we were then to take a segment and connect from the center to any one of the vertices, we form a segment there. We want to give that segment a name. We call these the circumradii, or this is for single a circumradius. Now, the circumradius, it ties together to our circle. As you see that if we break down the word circumradius, we've seen that prefix of circum. We've seen it in circumscribed. We've also seen it with circumference. And the radius, of course, ties into a radius of a circle. And here's why. We found that with our regular polygons that we are able to inscribe them in a circle, meaning that all the vertices of a regular polygon will pass through the points. That circle will pass through the points of the regular polygon's vertices. And because of that, that means the circumradius, because this point is the point from the center to the vertex, or the one of the vertices of our regular polygon, that the circumradius is actually the same length as the circle's radius. So as it turns out that the center of our circle is actually the same point as the center of our regular polygon. Now, of course, we need to show that this point is equidistant, and so you'll see part of the homework assignment that you will find the points to be, or these segments, the circumradii, to be of equal length. Now, there's a second segment that we need to introduce with a regular polygon. So now what we're going to find is, since this point, the center point actually exists, we can actually produce a second segment from it. Instead of a segment going from the center to a vertex point, we can actually produce a segment that is perpendicular to a side. So we use the center point as our starting end point of our segment, and we then produce a perpendicular from that segment to a side of our regular polygon. We want to give this segment a name, and we call it the apothem. So this segment here is actually a critical segment we're going to need to know the length of in order to actually find the area of a regular polygon. And so the apothem length, as we see, where we're going to find some true properties about it, and that's actually going to lead us into our next lesson as we derive an area formula. So in our diagram there's our center point C with the apothem drawn in. It's the perpendicular from the center to the side, right? It's perpendicular to the side. And we're going to let the lowercase a represent the apothem, which we'll talk about again in the next lesson, because that apothem has measure to it, has length to it, and that length is going to be used to actually help us find the area of the regular polygon. Now, there are provably true properties about both the apothem and the circumradius. Let's take a look at those. The apothem has two provable properties. The first thing is that if I were to produce an apothem from the center to every single side of a regular polygon, we can prove that all apothems are equal in length. Okay, all apothems are equal in length. And a second property we can prove of the apothem is that all apothems are going to be bisectors of the sides, meaning all apothems we can prove are going to be perpendicular bisectors, because by definition they are perpendicular, and by the property we'll prove is that they are bisectors. Down below we've got the diagram actually illustrating what we're going to prove, and that is, again, using our template of the hexagon. We find that all 6 of our apothems there are labeled with the hash marks to show they're equal in length, and that each of the apothems are bisecting their corresponding side. And you'll also see then, because we know all sides are equal in a regular polygon, that if you cut equals in half, you get equals, which means there we have the hash marks appropriately placed. Now, I do have one typo in here. As you notice, there is one of our segments there missing the hash mark. So there we go. I'll add that guy in there so he doesn't feel left out. But there we have it. We're going to prove these two properties to be true on our homework assignment. Now, there's one more property that we're going to be proving, and that's going to deal with the circumradius. So as it turns out, when you produce a circumradius from the center to any one of the vertex points of the vertices of our regular polygon, that circumradius is actually going to be an angle bisector. It's going to cut that vertex angle in half. In our diagram, again, let the hexagon kind of be our template here. So if we pick any one of the angles formed at the vertices of our regular hexagon, produce the circumradius from the center to that point, which is going to then cut that angle right in half. And once again, we know that all angles inside of a regular polygon are equal in measure, and because of that, we know we can say that if we cut equal things in half, that means all the halves are equal. And so from here, we find it's appropriate that I can use the single hash marks on every single one of those bisected angles. And again, that is a property we're going to need to prove to be true. So now the question we have to ask ourselves before we leave our notes is how? How are we going to show that these properties are in fact true? Well, how we're going to do it is through triangle congruence, of course. Triangle congruence is the foundation we started with our system, and it's actually one in which will carry us through this these properties to be proven about the apothem and the circumradius. Now, when you jump over to the homework assignment, everything has been laid out for you. Essentially, I walk you through the proof of proving these properties with filling in the claims for you, and you will give me the appropriate reasons. Now, when you're looking at the homework assignment as well, I want to fill you in on something you're going to see within the proof, or within the main theorem, I should say. So in computer programming language, you want to make this as human readable as possible, right? Because you may not be the only person who will be working on that computer program, right? Writing the code for this program. So what programmers do is they add commentary. Basically it's like kind of writing in the margins of a book. What they do is they will add commentary within the program so that anyone who picks up this code could read the commentary and know what a function does or why they have included certain lines of code. Well, I've taken this idea of the commentary and I've added it to the proof, because the proof is a very long proof. And the idea is I want to make sure you guys have the right direction of where to go in the proof. So to give you the right direction, I want to give you guys some commentary in order to kind of start you off on the right path. Now, how commentary works is this. The purpose of commentary is to be read, which means when you come across this line break and you find your commentary in there, the commentary will be denoted with a hash symbol. So it'll be the hash symbol followed by our commentary. It's what a typical commentary language is used, like in Python. It's one of the programming languages. So when you come across this hash followed by the comments, you're going to read the commentary. Don't just skip over that. The purpose of it is for you to read it, because I want to point you in the right direction of where the proof is going, so you're in the right mindset of what your approach should be. So again, when you jump over the homework assignment, you're going to see this laid out. It is really, there's two theorems. There's a lemma. Remember lemmas, those are helper theorems. So we prove a lemma real quick because it's going to be used in our core theorem to prove all these properties about the apothem and the circumradius. Now, how do we get away with this? I mentioned this just briefly earlier. We remember any polygon, regular polygon, can have any number of sides 3 or greater. So how do we get away with this? We're going to use a regular triangle as the foundation. And what we're going to find then is through the proof of the regular triangle, we can extrapolate that, and we can, if we find any other higher order regular polygon, that the pattern, or which I should say the procedure in which we approach with a regular triangle, we can then just extrapolate that for any regular polygon. So we can do that with a quadrilateral, regular quadrilateral, a regular pentagon, regular decagon, and so on, because now we'll have to add more information, but we're not adding any new information. It's just basically a repeat with the current process we have with the regular triangle, just repeated based on the number of sides that we have with that regular polygon. So as you'll see, we are going to be able to cover all cases, basically showing that these properties are true, that there is a center that exists, that center, we can produce these circumradii that are going to be angle bisectors, and we can produce these apothems that are all equal in measure, and that they are perpendicular bisectors of each respective side. So be sure to hop over, take a look at that 10.7 homework assignment. Again, we'll see using what we learned in this lesson to find the area of regular polygons in our next lesson, 10.8. All right. So if you do have any questions on that 10.7 homework assignment, do not hesitate to email me. With that, be good and do good.